We continue with our study of first order systems. Now, instead of constant inputs, we are looking at time varying inputs. Vs is a function of time, and the differential equation governing Vc is okay. Of course, Vs can be anything, but right now we are looking at an exponential, right? So, the idea is we know that the natural response of a first order system is a decaying exponential, and perhaps we feed that to another first order system, we want to see what happens. Okay. Now, what did we see? First of all, we know that this exponential is an eigenfunction of linear systems, right? So, it is quite easy to calculate the response as it turns out. We also kind of did it by using more rudimentary analysis by redefining the variables Vc minus Vs and one more linear combination. Finally, what did we get? Vc of t was, so let me explicitly show a peak voltage Vp. So, right, that was one part of it, plus what do we have? Vc of 0 minus, yeah, Vp by SCR plus 1 exponential minus T by RC. Okay. So, this is the forced or the steady state response, and this is the natural response. Okay. This is fine. So, the important thing to see from here is that the forced response to an exponential is exactly the same exponential scaled by some number, and that number depends on the frequency of the exponential. There is one parameter s in the exponential, it depends on that, and of course, some constants within the circuit. Okay. And this multiplying number here, this is the transfer function. Okay. This is fine. Now, while we did this for a first order system, it is quite easy to find this multiplier or this transfer function for systems of any order, right? Because if you have, let us say, I will still keep Vc as the variable. Okay. So, let us say we were looking at an nth order system where the highest derivative of the dependent variable is nth. It will be in general of this form, right? In our case, A0 was 1 and A1 was RC. Okay. And on the right side also you could have many derivatives. I will just take some example. This is the mth derivative and so on. So, we have, so sorry, this is A0 Vc, okay, and B0 Vs, right. This is a general linear differential equation of nth order. Okay. I will assume m is smaller than n, that turns out to be true in reality, m is less than or equal to n. Okay. Now, in this case, So, let us say Vs is an exponential. Okay. How would you find the force response part? The natural response, of course, you will have to find the natural response of this and then see. But force response, what would you do? Huh? So, we know that if Vs is this, Vc is going to be, the force response part of it is going to be some alpha times Vp exponential St. Okay. So, all you have to do is to substitute this there and substitute this over there, and what will be the result? Or maybe I shouldn't call it alpha, I will use it the normal notation, some h. What will it be? Please let me know. Please calculate it and tell me what is h. So, this is quite easy. What we get is okay. So, if you have a linear differential equation with constant coefficients, the transfer function will be in general ratio of polynomials in S, where S is the frequency of the exponential St, right. Is this fine? So, you would have seen these things already, but I am showing it to you nonetheless. Basically, it is the ratio of the force response to exponential St divided by exponential St. Okay. Because the force response, we showed it explicitly for a first order system, but you do know that just like an nth order polynomial can be written as a product of n first order polynomials, you can do the same for differential equations, right. You can have a differential equation, the first order differential equation, and the output of that goes to another first order differential equation and so on. If you do this n times, you will get, and eliminate all the intermediate variables, you will get an nth order differential equation. So, it shouldn't be very hard to believe that exponential St, its force response will be exponential St times something, right. Is this okay? I have left out some other fine print in the middle, but that is okay for now. Anyway, this was not the main point, we were only looking at first order systems. Any questions up to this part? Like I said, please go and derive this by yourself. Just by looking at it, you won't learn all that much. Okay. So, in case of piecewise constant, by the way, the piecewise constant stuff is already like it's a subset of this, right? Yes or no? How? What do you have to do? Is the piecewise constant case the one that we did earlier? Is it a subset of this, or is it is this completely different? Can you get the constant stuff from here? You understand the question? Earlier we solved it for a constant Vs. Now we have done it for Vp exponential St. So, can we get the earlier case from this? S equal to? S equals 0, that is all, right. Yeah, I mean, piecewise constant was just constant with different initial conditions, right. We did not do anything special for piecewise constant. What we did was solve it over each piece, assuming that it was constant, and then you solve it for that piece. At the end of that piece, you calculate the final condition, that will be the initial condition for the next part of it and so on. Okay. We did not take like the entire input together, right. Let us say if it switched from 0 to 1 volt at t equal to 0 and 1 volt to 3 volt at t equal to, let us say, 1 second. What we did was we first assumed that it simply switches from 0 to 1 volt. Okay. Using that solution, we calculated what happens at t equal to 1 second, and then that we use that as initial condition for another step at t equal to 1 second. Okay. So, basically the constant case can be got from this one. You do have the initial condition here also, right? Okay. So, if Vp equal to 1, S equals 0, this is like calculating the solution for a 1 volt step at t equal to 0. Okay. So, the earlier case is already included here. So, S equal to 0 corresponds to the DC or constant input. Okay. So, again something that you know, right? DC is 0 frequency, S equal to 0. And that is another sanity check you can use. If you do substitute S equals 0 here, what will be the transfer function? 1. Okay. For this particular case, the transfer function is 1. It means that in steady state, if you apply DC here, the same DC appears there. Okay. This we already knew also, because the capacitor becomes an open circuit in steady state, and then all of the applied input appears there. Okay. The natural response will have some coefficient which depends on the initial condition as well as the input. Okay. This was the case earlier also. The natural response depended on the input value as well. Okay. And like I said earlier, sometimes there will be, for a given input, there may be some interest in choosing the initial condition cleverly, so that there is no natural response at all. Okay. This is so that you get the desired response as quickly as possible. Okay. Any questions here? But this we also saw it does not work for S being minus 1 by CR. That is, if this RC circuit is driven by its own natural response, exponential minus t by RC, this solution is not right. So, what is the solution? Did you find it? I asked you to do this, right? Okay, please do it now. Take the total solution. So, define, so S becomes, and take the limit epsilon tending to 0 of Vc of t, and find out what it is. So, many of you have got this, of course. Basically, if you, this part there is no problem, right? I mean, it is only the part that has denominator of 1 plus SCR that has the problem. So, that we will have okay. The rest of it was, of course, there was no issue. Okay. And this, with the substitution, what do we get? This becomes epsilon. Okay. And here exponential ST would be exponential epsilon by CR times T, exponential minus T by RC, right. So, this can be factored out, and we will have exponential epsilon T by RC. Okay. So, it is the limit of this that you have to take for small epsilon. Okay. And you know that I mean, one of the ways to think about this is exponential x minus 1. Exponential x itself is 1 plus x plus some more things which go to 0 as x tends to 0 minus 1. So, you are just left with at x, right. So, what is the limit of this? As t go as epsilon goes to 0, t by RC, okay. This epsilon goes with that. So this whole thing becomes Vp t by RC exponential minus t by RC plus Vc of 0 exponential minus t by RC. Okay. Is this fine? Have you seen solutions of this form where you have t exponential minus t by RC? You must have seen it somewhere. Where is that? No? Damped oscillators. Okay. For what case? Yeah. Basically, when you have in a second order system, if you have the two roots to be the same, okay, you would get this. In general, I mean, we haven't discussed this at all, but since you already know Laplace transforms, you know that in the transfer function also, the denominator, the roots of the denominator are called poles, right. If you have identical poles, you will have this. If you have two identical poles, you have t times something, okay. If you have just one pole at some place, I mean, you should know this, right? You know or don't know? Have you discussed the natural response of some transfer function? The impulse response? Yeah. So, what would it be? 1 over s plus a. What is that is the transfer function. What is the impulse response? 1 over s plus a. Exponential minus at. Okay. And yeah, okay, fine. If you have 1 over s plus a squared, 1 over s plus a whole squared, 3 times. I mean, it's the same thing here. Okay, it's basically 1 over s plus a times 1 over s plus a. The first 1 over s plus a gives you exponential minus at. That is driven into another first order system with the same time constant 1 over a. Okay, so that gives you t times exponential minus at. Okay. So, of course, if you had I mean triple repeated roots 1 over s plus a cube, you would get t square and so on. Okay. So, this is the natural response, that is the natural mode, and this is the force response. Okay. Is this fine? I mean, again, for us now we just need to know, because this was the one case that was not covered by our earlier solution. So, it turns out that it is Vp t by RC exponential minus t by RC. Okay. Any questions about this? So, at least now first order system with any arbitrary exponential excitation, you know what the total solution is. Okay. So, it will be a combination of two exponentials, meaning it will have the input exponential st and the natural response is exponential. Okay. Those two will appear, but when the two are the same, what happens is that you will have this type of stuff, t times exponential minus t by RC. Okay. Any questions about any of this? And one of the most important things to do is to relate this to what you know earlier. This is not the first time you are looking at linear systems, right? You have already done a course on Laplace transforms and so on, impulse response of these systems. So, these are all related. Okay. In fact, at the end of this course, we will again redo Laplace transforms and we will see the relationship clearer, but you already know many of these things. Okay. For the what? No, the system is first order, the input is an exponential. Okay. So, if you now look at a second order system and its natural response, that is, you don't apply any input, you look at the natural response, it can look like this. Okay. Because, I mean, since you already know about transfer functions, I can talk like this. You know that the denominator polynomial in a transfer function can be decomposed into first order polynomials, right? So, I can think of it as a cascade or a succession of first order systems strung together. Okay. So, now let us say you have two of those systems, right? I look at the natural response. What do I mean? I do not have any input. I simply look at the what comes out, okay, from the initial states. Now, if I decompose that into two first order systems, I look at what comes out at the output of the first stage, that will be an exponential, and that is fed to the second one. Now, this case is no different from if I had only the second transfer function and I applied an input which is equal to what came out of the first one. Okay. So, this is what we would see. In fact, the natural response of a second order system would look like either this or the other case, okay, with some specific values for, sorry, yeah. So, it looks like either this one or that one with some specific value for s, which depends also on the internal components. Basically, it consists of two exponentials, right, exponential st and exponential minus t by rc. Okay. So, when we look at second order systems, we will see that you will have two exponentials in the natural response, or for some particular combination of values, you will not have two separate exponentials like this. You will have exponential, let us say p1t and t times exponential p1t as the natural response. Okay. So, in this case, we are looking at first order systems. Again, do not get all these things mixed up. Here, we are looking at first order systems excited by an exponential. So, we are getting two exponentials, one from the natural response, one from the input. Okay. Now, when the input exponential happens to coincide with the natural response, you will get that other slightly weird stuff where you have exponential minus t by rc and t times exponential minus t by rc. Okay. Now, when you go to the second order system, its natural response, that is with no input, actually looks like this. The second order system's natural response, that is with zero input, it looks like a first order system driven by some exponential. And it's kind of obvious, if you separate out the first order system into two pieces, the output of the first one will be an exponential. So, the natural response looks like the first order system driven by an exponential. Okay. And you can now build it up to higher and higher orders. Any other questions about this? So, now a first order system with arbitrary exponential inputs you should be able to analyze. Okay. Any other questions? Fine. We looked at constant inputs, we looked at exponential inputs, and in fact, constant inputs are subset of exponential inputs. You just set the frequency to 0. Okay, s to 0, you get the constant, right? And you can, by inspection, see the solution is the same. The transfer function will be 1 and you will get this. Okay. By the way, I have done this with Vc as the variable. You could take anything else as the variable, you will get the same, same result. The transfer function will of course be different. The post response part will be different, but the form will be the same. Okay. For instance, if I, yeah, anyway, maybe it's a good thing to do as an exercise. Let's say, please write the total solution for I1 with an input Vp exponential St, and let's assume for simplicity that S is not equal to minus 1 by Rc. Okay. What is the answer? How did you try to do this? Yeah, again, there are many ways to do this. So, Vs of t are so I1 is this, or maybe even easier is, right, you don't even have to differentiate. So, okay. So, Vs minus Vc, what that will give you is Vs minus Vc gives you Vp exponential St okay. Minus this whole thing basically. The one important thing is you get many terms. They will what? So, this is I1, right? Every term should have dimensions of current, otherwise there is something basic that has gone wrong. Okay. So, here this transfer function, it looks slightly different from earlier, SCR by 1 plus SCR, and this itself, everything inside the bracket has dimensions of voltage 1 by R, that is the current. So, however you do it, you make sure that this is the case. In fact, I strongly encourage you to write down the differential equation for I1, which you have already done before, and then write it from there. That should also be quite easy. Okay. And of course, for constant inputs, for S equal to 0, you should get the right answer. Okay. What is it? What is I1 when Vs is a constant and the initial conditions are 0? Yeah, what is it? What is the solution? What is the initial value? Yeah, Vp by R, and then Vp by R exponential minus T by Rc, and that is what you do get here. Okay. And if we see there is an initial condition, that gets subtracted and so on. Is it okay? So, you should be able to write it for any first order system, okay, but just do not make elementary mistakes, and make sure that the dimensions are all correct, because we have S and many other quantities here. What is the dimension of S? Frequency, that is frequency, right. Any questions about this? So, now any first order system with this exponential type of time varying input, you should be able to find the complete solution. Okay. So, we have done constants, we have done exponentials. What other kind of input should we deal with? What is that? Sinusoids. Yeah. So, that looks like also a common enough case that you may want to do that. Some general sinusoid, Vs is Vp cos omega t plus phi, and again I will write the differential equation in terms of this Vc that is the differential equation, right. The forcing function is Vp cos omega t plus phi. How would you go about solving this? Exponential, right. What as sum of exponentials? Okay. No, okay, one at a time. So, what do you want to do? Okay. So, you use the complex expansion for this, right. So, this is exponential j omega t plus phi plus exponential minus j omega t plus phi divided by 2. Okay. So I write it like that. Then what? After this, use linearity, meaning, okay. So I analyze it with this first and then that one. Okay. So what will be the solution with this? I mean, why did you even suggest this? Is this easier? We can take e to the j5. Okay. So basically the point is we have already done the solution for an exponential. So reducing the sinusoid to the combination of these two complex exponentials seems easier. Is that the logic? Will this work? Okay. Fine. This will be fine also. So what we have to do is find the solution to Vp exponential j omega t plus phi. Remember, inside it is not of the form exponential st, but this is just a scaling factor which is Vp exponential j phi exponential j omega t. Okay. So now this becomes the scaling factor for this exponential. Okay. So this is of the form Vp exponential st, or maybe I will call it Vp prime because this Vp is different from that. Okay. You find that and repeat for exponential minus j omega t plus phi. Does this look fine? Is this fine? Okay. Any other possibilities? Let us say you didn't want to venture into complex numbers. Okay. Derivative of cos is sine and derivative of sine is cos. So what? Basically all this differential equation solution business is guessing, right? I mean, you guess that the solution will be of this form and check if that is correct. So for the exponential, that's what we did. If you differentiate an exponential, you get an exponential. So that will be the solution. Only thing is you have to find out how much of an exponential that is, right? So alternatively, if you want to stay in the real numbers with real sinusoids, you could also do that. What would you assume for Vc of t in that case? What would you have to assume? Can you do it or not? Is it possible? What? Yeah, basically we need to consider both sine and cos, because on the right side we have only cos, but of course with some phi inside. So now on the left side we have Vc as well as its derivative. So if we have Vc to be a sine, we will have cos, and if we have Vc to be a cos, we will have sine here. Okay. So if you want to get only a cosine here, then you will have to have both. Okay. So in general, you could also do it in another way. Assume that Vc of t is some alpha cos omega t plus beta sin omega t, and then you substitute it into the differential equation and find the constants alpha and beta. Okay. So that it satisfies the differential equation. Okay. So here you have two constants. What about there? No, I mean here you have to determine two constants. What about in this case? If you use the complex exponential. Did you understand the solution, or should I just make you do it? You don't have to do anything? Okay. So fine. So these three rows, please do it with this complex exponential. What I want is the final solution Vc of t equals, okay, and similarly those two can do it with this. It's I think of similar complexity. I mean, if you want, you can also assume solution of the form. I mean, put this plus 5 here. There is no sanctity to that. It's general, even without it. Okay, please complete this by tomorrow's class, and it's probably just 10 minutes of persistent algebra. That's about it, but make sure that you complete it. And I want the complete solution. That means the forced response and the natural response. Okay, and of course, do your sanity check. The natural response, for instance, you could set omega equal to 0 and then see what happens and so on. Okay, omega equal to 0, phi equal to 0, you get a DC input, and whatever response you get should correspond to what you already know very well for DC or constant inputs. Okay, so please do this. We will continue from there, and then also think about if there is a more convenient way to do this. I mean, I think the algebra was slightly annoying, right?